statistical significance is dead. Wait, you may think, but we need statistical significance. Well, what should we do without it? At least you all use it until today, or most of you used it, because we have distributed this survey, and actually we received 40 questionnaires back. And of these 40 questionnaires, 37 persons indicated that they use p-values, and of these 35 dichotomized them into significant and non-significant. So we ask you, why do you do that? And then we try to categorize your free text answers into 3 meaningful categories. Most often you mentioned that statistical significance helps you or tells you something about the reliability of your results, so that when you get statistical significance, you can be sure that you have something. Also, very often you mentioned that the research community wants it. That includes the journals and the nasty reviewers, and some mentioned also supervisors. So you also use statistical significance because others want it. And what was surprising here, that only 3 persons indicated that significance helps making decisions, objective decisions. Because, well, I personally expected that this sort of answers would be given much more often. Well, so you use statistical significance. And then we ask you, how do you imagine clinical research without statistical significance? And these free text answers we try to represent in a word cloud. And actually, I was surprised that this doesn't look as apocalyptic as I expected. Though you often mentioned that, oh, well, this will be difficult, and well, we don't have any other alternative. It will be confusing. That's not possible to do, and so on. You also mentioned positive things. So you say that, well, it will be good and more patient relevant, and we will focus more on estimation instead of just dichotomization. And my favorite of these answers is, where is it here? That would be paradise. All right, so, but either way, the era of statistical significance has come to an end. So therefore, I would like to have a quick and incomplete look back at the life of statistical significance. So it's not that clear when it was born, but we start in the late 19th century. So imagine a man watching wasps, watching how many wasps fly out of the nest, how many come back, counting these numbers over several days, and also recording the weather and other things. Now, this man was Francis Edgeworth, and he observed these wasps because he was interested whether there is a difference in the behavior or the trade activities of these wasps between different days. Now, he was not a biologist, as you might think now. He was an economist. And he thought that if there is a law of trade that we humans use, you should also use indications for such a law in wasps, because they are also trading, sort of. Now, he was not only interested in economy and wasps, but also all kind of other things. And he wrote a long paper about methods to use to find out whether differences between means are accidental or indicative of a law. So finding out whether there really is something or not. And he used the term of real significant differences. So significant in the meaning of being meaningful, right? Now, this isn't too bad per se. So the bad things happened a few decades later. I'm sure you've all heard of the famous statistician Ronald Fisher. He introduced the procedure of significance testing. So he developed or proposed the concept of p-value and testing of this p-value. And he wrote something very notable in 1933. He wrote that it is usual and convenient for experimenters to take 5% as a standard level of significance. So does that ring a bell? I guess so. So that's the level of significance, the 5%, the p-value smaller 0.05 or not. And the reason to choose this is not something mathematically complex or deeply founded wisdom from science, but because it was usual and convenient. And I'd like to emphasize that Fisher was not dealing with clinical research or human lives. He was mainly dealing with agricultural experiments, so crop harvest and things like that. Yeah, and he also said that take this as standard level of significance and be prepared to ignore all results which fail to reach this standard. So either you reach this level of significance or forget about it. Now, Fisher was heavily criticized also at this time. He had many admirers, but also many critical voices were raised. And probably his most prominent opponents were J.C. Neyman and Egan Pearson. For example, they say, yes, you only care about one error probability. You do not care about power. How big is your experiment? And so on. Now, Fisher didn't like being criticized. And these guys didn't like being ignored. So in turn, they ignored Fisher as well. And they developed the concept of hypothesis testing, while Fisher developed the significance testing. And they used different terms that sound similar to us now. So Fisher, we have the null hypothesis and the p-value and the significance level. Neyman Pearson called the analogous to this the main hypothesis and the alternative hypothesis. They talked of alpha and beta and sample size and test statistic that you compare to a critical value. So while these were different concepts and these gentlemen kept on arguing, other people, mainly non-statisticians, mixed these two different concepts, picked out things, and merged it all together into something which we know as null hypothesis significance testing. And that's the really bad thing, right? Because this led to the question asking of, is it statistically significant? Instead of asking, how big is my difference? And it also led to the misconception or interpretation of statistical significance, indicating proof of an effect, or that statistically significance means the result is important, or that you can make a scientific claim about the truth. No, this all is not true. So one more amusing consequence of this chase for statistical significance is that when people fail to get p-values that are significant, when they are just not significant, they can become very creative in describing their results. And these words are all from this website. Have a look at it if you need something amusing. Yeah, just three of my favorites are results or p-value flirting with conventional levels of significance. And one person had a near miss of statistical significance, and in one case, they just barely escaped significance. Yeah. So, but this somehow indicates that this black-white thinking, yes, no, doesn't make that much sense, right? You see your data, you think there is something there, but it's not that strong that it gets statistically significant. So this just indicates that black-white thinking is not really in our nature. So while this is more amusing, the more serious consequences are that what we know as p-hacking and reporting and publication bias because of this chase for statistical significance, and because everybody thinks that the editors, reviewers, and the journals, they want significant results. And not surprisingly, we have a reproducibility crisis. And 3 years ago, the American Statistical Association, which is the biggest statistical association, decided that this must come to an end, and they wrote a statement based on the opinion of several experts about misuse and misconceptions of p-values and statistical significance. So the main message, or one of the main messages, was that you should emphasize estimation over testing. So ask, how much is my difference, and not whether it is significant or not. And 1 year later, in 2017, they had a conference in order to gather ideas what to do instead, because it is quite obvious what we should not do, but what should we do instead? And the result of this conference was published 2 years later, so last year, in a special issue consisting of 43 papers. And the title of this special issue is Moving to a World Beyond P smaller 0.05. And while the opinions differed, there was one sort of consensus that emerged from many of these papers, which is that it is time to stop using the term statistically significant entirely. So let's put statistical significance to a rest and be brave and step out into the world beyond P smaller 0.05.
Yes, thanks for inviting me. I'm neither a statistician nor a physician. I'm a zoologist from the Vesalianum, which is just in the neighborhood, actually. And I guess the reason I'm here is that I happen to be author of this paper. looks a bit weird on the screen here. So if you did not see it yet, it's very short. It's a commentary of 2 pages in Nature that caused quite some uproar because it was signed by 800 signatories. And nothing we say here is new. Actually, it was said the first arguments against statistical significance were even before Fisher. It's now, I think there was a psychological paper in 1919 writing against statistical significance already. And I could tell you a long story about how I came to write this paper. Perhaps to cut it very short, I'm one author of one of those papers in the special volume of the American Statistician that was presented by the ASA. And so I got invited for some strange reason, and doesn't work. Oh, take this one. So, and the main ambition behind our paper was that everybody was really upset about something that happens a lot in every second journal article, including my own article, I must say, that I wrote as a zoologist. People use non-significance to say there was nothing. That just comes so natural, and it also comes because Neyman and Persson themselves, they said either accept a null hypothesis or reject it. And this accept we frequently misunderstand as saying, well, then there's nothing. Effect is zero. And why this is wrong? That's, of course, could be the topic for an entire lecture, actually of several hours. I'm going to show you 2 examples that have been published in JAMA. And this was the funding source of this Nature article, actually. When I got in contact with Sander Greenland and Ken Rothman, also epidemiologists, they hinted me to this paper. It's about antidepressant use during pregnancy and autism. And this was the example we actually wanted to use in Nature, and then they said we should not use it because it's so politically loaded. So now there's another article, another example. But I'm nonetheless going to quickly lead you through this example. So they say the association was not significant. They give a hazard ratio of 1.61, so it's a 61% increase in hazard. They give a very nice confidence interval that, well, it's it barely escaped statistical. No, it did not barely escape. It actually, no, of course. So probably they tweeted, they put it in this way to, well, it's almost zero. So it's basically from no effect to a vital effect of 159%. Hazard increase covered by this confidence interval. Then their conclusion is compared with no exposure, not associated with autism spectrum disorder in the child. Now my colleague Sander Greenland published a preprint last year in which they nicely show why this is rubbish. It's simply not true. So it's a so-called p-value function, or we can also call it confidence curve or compatibility graph, and it shows you that the compatibility interval, that's just a new name for confidence interval because we don't like to have confidence. What we say is this interval covers values that are compatible with our data given our model, and the main problem with this word is that neither I nor my students can actually pronounce it. So otherwise, I really like it, so I really try to use compatibility graph in the future. So that's the 95% compatibility interval from about a hazard ratio of 1 to this increase of 159% hazard. And you can see that if we test each of those values on this axis using our data, we get, for example, a p-value of 0.05, which is what they actually found, for the hazard ratio of 1. So the null hypothesis gets a p-value of 0.05, and that's usually what we test. But we could as well test any other point in this interval. For example, the point that we actually found, the observed hazard ratio of 1.61. If we test this, it gets a p-value of 1. That's by definition, if we test our observed effect, it will always have a p-value of 1, and therefore it's the most compatible value with our data. So what we propose is a more correct description. given our model, our estimate was this hazard ratio of 1.61. You can also frame it in words that everybody will understand. So it's a 61% increase in hazard risk. It's not zero. And second most important thing, that's why somebody wrote on those very nice t-shirts, I embrace uncertainty, because this is, of course, the thing that matters, to interpret the endpoints of our intervals. And this means that we should write under the same model, so everything is, of course, based on some model. Every hypothesis from no increase up to this 160% hazard increase is highly compatible with the data. And that's not the only values that are compatible with the data, because there are also lots of values outside this interval that are compatible with our data. And the conclusion should be, it's an imprecise result, of course, because we have a wide interval, and these results are most consistent with what other studies have found, because actually other studies have found about I think a 70% increase in autism. So, and what was later in the press, so Medscape, probably most of you know Medscape, of course they say no link to autism, because that's what the authors misinterpreted. And we think this is a scandal. Quickly, second example, without going into the details, it's about screening methods in septic shock. And here we have a hazard ratio of 0.75, meaning a 25% decrease in one treatment compared to the other treatment. Then we have again an barely escaped, significance, a p-value of just on the other side of this arbitrary threshold. And just as a side note, Fisher himself said this is completely arbitrary, this threshold. But somehow everybody knows it, but somehow we still use it. And also conclusion did not reduce all-cause mortality. Then this was last year, actually. Ken Rothman, epidemiologist, replied to a tweet by David Spiegelhalter, one of the most famous statisticians in the world. You can read it yourself. It's appalling, he says. And Ken Rothman, of course, says, can kill people in this case. And then he asks a question, and that's in the next tweet in this row. Oh, sorry. So, of course, what we should be concerned about is not a p-value threshold, but what are the costs and benefits for our patients? And he says, if you were a patient with a septic shock, which treatment would you prefer, independent of the p-value? So I know what I would be doing, I guess. So you could say this is all not the fault of the significance threshold, it's the fault of us. We just behave badly and misuse it. But there are issues with statistical significance itself. And here's just one. I could present you again several hours of talk, of course. So we have an effect size inflation, or I prefer usually the very colorful word truth inflation. Statistically significant effects are almost always inflated effects. If we pick out of a long list, and we've seen several of those lists today, if we pick the effects that are significant, we are actually not telling the truth. In most cases, we are overestimated effects. And you can see this actually not only theoretical, but also in replication studies. This is probably the most famous replication studies of the last decade, 100 psychological studies. Original results, of course, all significant. Replications, of course, many of them not significant, so p-values from 0 to 1. And you can see that this coincides with effect sizes. So the original studies had effect sizes that on average, the median here, were double as large as the replications, and that's what we always see. So usually the first studies on some topic have much larger effect sizes than replication studies. Second thing, we all tend to overestimate by far the reliability of our significant studies. And this is a quite old study now. It's a meta-analysis by Ioannidis, showing very nicely the dance of confidence intervals. So you can see intervals covering the null value of a risk ratio of 1. Of course, non-significant, significant, non-significant, significant, non-significant, significant, non-significant, and so forth. So it's no use to publish any of those studies and saying I found something or I found zero, because the next study will find something different. And of course, what is worthwhile looking at is then the meta-analysis here, just the effect size over all those studies, but be aware that also, as we now know, the same dance of compatibility intervals, confidence intervals, or p-values also applies to meta-analysis, of course, because the studies on which those meta-analyses are founded suffer a lot among publication bias or among all those issues I'm talking about here. So, wrap up from my side, decision-making under uncertainty. Let's try to keep in mind that, first of all, the thing that we observe, the observed effect size varies a lot. We call it the dance of effect sizes, and if the effect size varies, of course, also the p-value varies from study to study because it's calculated from effect sizes. Also, the confidence intervals dances around a lot because it's calculated from p-values. So the question we should ask, nonetheless, is what did you observe? And we should describe it without saying this is the truth and the next study, well, will show also a different truth, of course. We should describe what we found, and most important, we should try to embrace uncertainty and try to start describing the limits of our interval estimates. Most important of all, and that's, of course, we all know that, at least as important as our study are all the other studies that have been already published. We should look at biases, and preferably not at the ones we know, because these we can try to account for. Usually the problem with biases are the ones we don't know, because we did not account for them. And we should leave this open and try to at least have some discussion about what we could have missed. And if you are a physician and must make decisions under uncertainty, of course, we need to look at the risk for our individual patients. Okay, this was my part. Thank you for listening.
Thank you very much. So we have heard its statistical significance is probably really dead now. So it was a tool for us for many years, not for so long, but let's say almost 100 years. And of course, you must now think, how does it go on? How could it go on? If you read these 43 papers, there is not a clear answer that everybody agrees on, but I think there is something that you can clearly read between the lines, either or really directly, and that is why we put it also on our T-shirts. We need to much more embrace the uncertainty behind what we are doing instead of dichotomizing into statistically significance or not. But let's take a step back and look what we are actually doing also in clinical research. So normally, if you want to improve something and have a new treatment, I depicted this here in red, we gather a number of patients or participants, can be quite a lot, and we take one group with a traditional treatment here in black, and we take a group with the new treatment here in red. And then we look on a hopefully important, patient-relevant, good measurable outcome, whether there is a difference between the new treatment compared to our old treatment, and whether we can separate these two at all. Now, if this difference in the outcome is quite big, we can quite easily separate these groups by eyes, I hope. It becomes a little bit different if the difference is a little bit smaller. You see, the new treatment is still better, but these two groups, they don't separate very well if you look at them. It becomes worse if you don't take a huge number of persons, but only a small group here, only 4. Then even a big increase in the outcome might look, yes, they separate, but there's quite some overlap, no, compared to the number of persons you observe. And it becomes much worse if the difference is, of course, smaller. On the other hand, if you observe an intermediate number of persons, but they have a huge spread in how they react to the traditional and to the new treatment, even with a big difference in our outcome, we have quite a large overlap. And it becomes, of course, much worse if the difference is smaller. This is better if the same number of people don't show a big spread, so they all show the similar result. So with these ingredients, you see, we can sometimes separate quite well our groups, the new treatment from the old, but in other cases it's quite difficult. So the ingredients we have to separate our two groups are the effect size, whether there's a big effect or only a small effect. Another important ingredient is whether we have a big sample size, we study thousands of persons or only a few, and of course whether these persons all show the same reaction to the treatment or whether there is a big spread in the reaction. Now this whole information, these ingredients, we can compress them and tightly summarize them to something we all know, which is called the p-value. It's a continuous measure which tells us how well we can separate what we have seen before. It goes from 0 to 1, and as I said, it's a very tight summary of all this information. And now what was very often done until last year when statistical significance died, is that we even more summarized this number, this p-value, and said, okay, let's cut it into bigger or smaller than 0.05. So we have a black side. If it was smaller, it was a negative study. We couldn't show a difference. Or we have a significant result and we could easily publish our results because it was a positive study. Now, this is all fine. You can argue whether it works. In some very few restricted situations, it perhaps even makes sense. But the most problematic thing is if we now step a little bit back and we take our significant result and ask ourselves, what does it mean regarding our ingredients? If a result is significant, does it mean that we have a big effect? Oh no, it doesn't mean that the effect is big. It could also be that we had a huge sample size or a very small spread. So you cannot interpret what you get here by looking at the ingredients. And the other thing is true as well. If the result was not significant, this doesn't mean that the effect was small. It could be that there's a huge effect, but you had not enough sample size or the spread was simply too large. Now, if we turn the wheel of time, of course, the ingredients are still the same. So there are no new ingredients just because statistical significance is dead. But we should put a step of interpretation in between and stress this step. We should estimate how big the difference is between the treatment and the control in the easiest case. And we should have a look at the uncertainty, which comes from the sample size and the spread that we observe within our groups. If we really want, we can further summarize this information to a p-value. But what we will not do in the future anymore, because it is dead, sorry, we won't dichotomize this p-value into significant and not significant anymore. So if we look at these scenarios, so the old world and the new world, it becomes quite obvious what needs to change. We need to really care about the estimate, how big is the estimate that we observed, and we should not forget the uncertainty. And the uncertainty should not be something bad. The uncertainty should be something that we look at, that we discuss, and that we embrace in a certain way. Now, how could this look like if we do it? And it could look like something quite familiar to us. We can stress the estimate that we have by looking at the difference in our outcome, and we can depict the uncertainty. Valentin said we can use a compatibility interval, confidence interval. I'm sure in the future there will be other measures of this uncertainty that we will use. But I think the most important point, if you look at this figure, is that we look at the difference in the outcome, and this difference in the outcome normally has a unit, because we choose this outcome. We don't just take any outcome. We carefully choose this outcome. So it has a unit, which means we can interpret this outcome. We can tell whether it is big or small. And that's our responsibility as researchers to say, we found a difference of whatever, and this difference is as big or not, or etc. as we want. So we need to discuss this estimate, and we need to discuss the uncertainty that we always will have with this estimate. Now, this tool, this statistical significance, is dead. And I think something that is very often forgotten, if we talk here about a method, a tool. So, and whenever you use a method in clinic, everyday practice, you always think about the risks and the benefits of these methods and of these tools. And there are 43 papers only in this ASA series, and there are much more risks and benefits of this technique, statistical significance. And you can discuss what is the better one, has this benefit, has this risks. But as Valentin has shown, I think quite nicely, and thousands of publications have shown, this discussion whether the risk or the benefit of this technique, of these tools, is more important, is just dominated by something that we see every day if you browse through a scientific journal, and this is the misinterpretation of this concept. And for me, this is reason enough to say, okay, goodbye to statistical significance. Thank you.